So today we have David Jaz Myers from Johns Hopkins talking about open dynamical systems.
Hi everybody, I'm David. So I'm going to be talking to you about a general definition of open dynamical systems. So I'm going to do something that's a little strange for a category theorist in this lecture, which is I'm going to give you a definition of an object, an open dynamical system, but I'm not going to tell you what the morphisms are, and hopefully I'll be able to come back and tell that story sometime. I'm also going to be using the technical terminology or the technical machine called the Grothendieck construction. So I'm just wondering if I could get a show of hands. Who's familiar with the Grothendieck construction and what it does? Okay, so I might go over the idea of it, but I think for interest of time, I'll take it as known. So a dynamical system is an idea of how things could be, and given how they are, how they might change. Now, there's a lot of different specific instances of this general notion. So one of them is what we might call a discrete-time dynamical system. Discrete-time. And discrete-time dynamical systems take place in various sorts of categories. We might say the category of sets, or the category of topological spaces, or the category of measure spaces. And the dynamics of a discrete-time dynamical system is pretty simple. We have a set S of states, and these are the ways things can be. And then we have an evolution operator E, or for future reference I'll use U for update, S to S. And this lives in that category. So if we're working in the category of sets, this just says, given a state S, I will now transition into the state US. If it's in topological spaces, it says that this operation is continuous in S. And if it's in measurable spaces, it says that the inverse image of a measurable set is measurable. Or, depending on the category, that this operation is measure preserving. So in ergodic theory, this is the most common category. So that's the basic, most simplest doctrine. So when you first see the notion of dynamical system, you probably see this notion. But there's a lot of other notions of dynamical system that appear very commonly. And for example, we might have a probabilistic or Markov process. So probabilistic. Not actually sure how to spell that word. Or Markov. And this takes place in the base category is set again, but now we're not going to take any state to the next state. We're instead going to take this state to a probability distribution on states that we expect it to transition to. So in other words, this is of the form U from S to ds, where D is the set of probability distributions on S. So this is also known as a stochastic matrix. Because for every pair of states S and S prime, one S living here, one S living there, we get a number between 0 and 1 telling us how likely the system is to update from state S to state S prime. Now we also have maybe other ideas of dynamical systems. Sometimes we want an update that is non-deterministic. In other words, we don't know how to quantify whether it will transition. We just want to know whether it's possible that it will transition. So this is non-deterministic. And that also lives in set. And here, our update sends us from a state to now the power set of S, in other words, the set of possible states it can transition into. And finally, we have maybe the most important notion I'll talk about today, which is continuous time dynamical systems. And this lives in a continuous sort of category. I'm going to take my category to be manifolds. And the operation here is traditionally given by a differential equation. So a differential equation here might be of the form ds dt. In other words, where s is our state, we're saying where is our state changing? Well, that's given by some function of s. And the way we encode this as a morphism is we want to take, can everyone see me down here, or is it too low? I'll bring it up a bit. Whoop. We want to take our state and we want to give it a tangent vector, f. And we want that to be over s. So in other words, if this is the projection here, what we want is a vector field on our state space. And so that is a section of the tangent bundle, and it looks like this kind of triangle. So the way we read this is f is really a vector field. It sends every state to a vector, which is fs. And then this differential equation is the differential equation that tells us how to integrate this vector field into curves. And those are the solutions. Those are the trajectories of this continuous system. So these are all closed dynamical systems. They, at the outset, when we model them, we've set up the dynamics. In the state, it will do this. This is how it's going to change. But real systems in the world are often not really isolated this way from their environment, from the outside. The outside can influence them, and they can influence the outside again. And when we try to make interactive systems, systems that can interact with the outside world, and we want to make them in a modular way, we need to understand really well how dynamical systems can interact with the outside world, and not just how they evolve on their own. And so this is the idea of an open dynamical system and why we want open dynamical systems. So my dad always likes to say that all things always eat, and then they hold, and then they poop. And that's the basic idea at the heart of an open dynamical system. You have a way to eat from in your environment, you have a way to hold what you eat, and then you have a way to poop it back out into your environment. And so this is the basic idea underlying an open dynamical system. So I'm going to tell you a discrete-time open dynamical system, or this is also known as a deterministic automaton. So example, discrete-time open dynamical system. And I'll just call it automaton, or deterministic automaton for short, because discrete-time open dynamical system is a bit of a mouthful. So what does it have? It has a set of states, S, which is the ways it can hold. It has a set of inputs, I, which is the things it can eat. And then it has a set of outputs, O, which is the things it can get rid of. All right. Now, there's two basic ways that these connect. One is there's what we would call a readout function. So a readout, which takes a state and gives us an output. And then there's an update. And it takes a state and an input, and it gives us a new state. And so this is the basic framework of open dynamical systems. They're always going to have these three components, states, inputs, and outputs, although the particular kinds of things these will be might be different. And they will have two sorts of morphisms or functions, the readout and the update.
There's no possibility of feedback because the output does not affect the transition.
Well, this is a single dynamical system, but in order to have some kind of idea of how they interact, we have to have multiple of them. So we'll write a single system like this as a box with an input on the left and an output on the right, like this. So now we can talk about a basic idea, a basic feedback, a basic idea of open systems interacting. Suppose that we have where do I want to put this? Suppose we have over here, so I'll say example is agent, environment, interaction. So suppose we have these two dynamical systems. I'll call it the agent, and the agent takes in a result and gives out an action. And then we have the environment. And the environment takes in an action and yields a result. So to recall, each one of these has these two functions. And I'm just going to label them by their, I'll label this one by R sub A and this one by R sub E. And I'll always use R and U to determine these functions for whatever I'm talking about at the moment. So one way I could have these interact is I could say that the agent gets some information from the environment and then does an action. And meanwhile, the environment takes that action, changes, and gives some feedback to the agent. So I can turn these into a single dynamical system, which is closed. And that system will have this dynamics. So its set of states will be, so the whole system is the agent-environment interaction. It's a closed system. And it's going to have the agent states and the environment states. And they're just going to update together. And this is how they're going to work. If I take an agent state A and an environment state E, I'm going to get a new agent state and a new environment state. So what I want is that the environment takes the action that the agent is doing and updates, and that the agent takes the reaction from the environment and updates. So the new agent state here will be the update of the agent on the agent's current state and the result of the environment in its current state. And meanwhile, the environment is going to do the same. It will take its current state and the result of the agent, the action that the agent does in its state, and it will update. And matching parentheses says one more. Right. So this formula here is a little cluttered, right? What we want is a more formulaic way to have this idea. Now, there's a really simple way to get this idea across, which is that here we have these two boxes. We could wire them together. So this is agent, environment, and we want that the agent's action affects the environment, but we want that the environment's reaction affects the agent. So what you see here is we've made this full boxing. And this wiring diagram, which is what we'll call these kinds of diagrams, expresses the same information as this formula. And so what I'm going to tell you about now is how we wire together these dynamical systems. And this will give us a sense of how we're going to come to this general definition, because to do that, we're going to need to know how to wire together these systems in order to figure out exactly what it means to generally wire them together, and then generally how to define them in all these different contexts. So, I'll flip this around. talk now about wiring diagrams. So this is called a wiring diagram. In general, they look something like this. You have a box, it has some inputs, and it has some outputs. And now every box can be filled either with a system or with a bunch of smaller boxes wired together. So we might wire together boxes like this, and then they can be wired together in this way. So this, and maybe they have a little bit of feedback loops and things like that. So there are a few simple rules that let us draw these boxes. So here are the rules. Rule 1 is every outer output connects to an inner output. So that means that if I'm out here waiting for this system, the outer box, then I'm actually going to get something that's coming from one of the inner systems. And rule 2 is that every inner input connects to either an inner output, which allows for feedback and connection, or an outer input. So you can verify that this satisfies that. Now see, I never said that every inner input is going to get hooked up into the system. We might just take it in and forget about it. But every inner input here has to get its information from somewhere. Every system in there is waiting for an input in order to update. So it needs to get it from somewhere. And so the rule says it will wire to somewhere. Now these two rules can be expressed in terms of functions. Functions between finite sets. So every box here, so a box consists of a finite set, and we'll write it like this: B out, B in. And both of these are finite sets of output wires and input wires. And then if we have a finite set of boxes, so let's say, suppose let's say A1, dot, 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 A in, N, A out, N. Suppose we had a bunch of boxes, A1 through AN, and we wanted to wire them into a box B. Well, if I let A with unadorned by this thing, so if I let A in equal the sum over I of A, or I'll say the disjoint union over I of AI in, and similarly for out, then these two rules can be translated into functions in this way. A wiring diagram is going to be a pair of functions, W out, W in. It's going to go from A in to A out. And it's going to consist of these two functions here. W out is going to express rule 1. So it takes an outer output to an inner output. W2 expresses, W out expresses rule 1. W in expresses rule 2. So W1 takes an outer output to the inner output it's wired to. W in takes an inner input and takes it to either, this is disjoint union plus or coproduct, the inner output it is wired to or the inner input it is wired to. Uh-oh. That again.
This may be better.
Oh, thank you. Okay, so these are the rules for drawing our wiring diagrams. Now, how do we compose wiring diagrams? Well, one really cool thing about them is that since this outer box really is just a box, and all these inner boxes are just a box, what we can do is we can actually just put new things in here. We can fill them in like that. And so in other words, the way you compose wiring diagrams is by filling in the boxes with the other wiring diagrams. So if you're familiar with the idea, this is a sort of operad. And so what you do to compose a wiring diagram, I'll draw that here, you take an inner box, and then you put more boxes inside it. And then you remove the middle layer of boxes. And now you see that what we're left with is another wiring diagram. Now, how this looks formulaically is this. If I have A in, A out, via W1 in, W1 out, to B out the in, to W2 in, W2 out, then their composite is going to be defined like this. First, I'm going to follow along the outer ones in. So what that means is I'm just going to compose these functions here, W out. I'm going to compose them together, and that's going to take me from this outer one, maybe if I draw the inner boxes in here like this again. I'll follow this outer one here to this this middle output, and then keep following it in until I get all the way inside. So what that is down here is it's going to go C out to via W2 out, B out, 2 via W1 out, A out. Now, the next one is a little bit more involved because here we have to case split. But we can still do it just by composition. So the way this is going to work is this. We're going to take an A input here. So that's an inner input. And now we're just going to follow it along. But it's going to be a little bit of a longer route. So first, we'll take an A input, and it either goes to an A output or a B input. But now that B input, that's a middle input. We want to keep going. So that one's going to go to out plus W2 in. That one either goes to out plus. That middle one goes to either a B output or a C input. Now a C input is fine. That's an outmost input. That means we followed along this wire here and we got all the way to the outside. But if we were here, we followed along here, it went back here. And we have to keep going to get back all the way on the inside. So what we do is we compose again. So we have B out. We can get from there, this was optimistic, we can get from there to A out plus A out plus C in plus W1 out, C in. And now here, I just have A out and A out. What does that mean? Well, I've double counted. I have two different ways that I could get an inner input now by tracing along. So I just want to ignore that. And so what I'm going to do here, I'm going to use what's called the codiagonal, which just sends them both to the same thing. And this finally gets me all the way to my desired end here, which is either an innermost output or an outermost input. Okay, so that's a mouthful. It's not really fun to check that this is a category, as it is, right? Because it's a mess. But if you are familiar with the notion of Kleisli composition, this might look kind of familiar. So if you've programmed in Haskell, you probably are familiar with the notion of Kleisli composition. It's the do notation. It's the monad composition. So what we're doing here is we're using the either A out monad. And that is handling all of this composition. But there's a little twist. And that little twist is that what we're eithering here, either is the Haskell word for this coproduct, I should say. What we're eithering here is A out here, but then we also have the B out here, which is not A out. We have to go back to A out here. So it's Kleisli composition with a twist. It's Kleisli composition indexed over different objects of the different outputs. And so that's the notion we'll come to now. I hope you all remember what a wiring diagram is. Okay, so what we can see then is that this looks a lot like Kleisli composition. So we have a functor called Kleisli plus, and it goes from finite sets it goes from finite sets to categories. And it takes every finite set C to the Kleisli category of the monad C plus dash. So is this concept familiar to people here? I'm getting the sense that I should explain what this is. This is a category whose objects are the same thing as finite, but it has different morphisms. These morphisms come with extra effects, which is the Haskell way of talking about this. In other words, what is a morphism here in the Kleisli category? It doesn't go from x to y. It goes to x to c plus y, c or y. And composition looks like this. We go to c plus y, and if we had one from y to c plus z, we would go to c plus z. But we've gone too far. We have too many c's. We got to go back. And so we use the codiagonal to go back. And you can see that looks a little bit like this one here. But again, we missed this middle part, right? Where we took the b and turned it into an a. So the way that works comes from the fact that this is a functor into categories. It's what we call an indexed category. Oh. Given a map from C to C prime called F, we can send a Kleisli morphism here to the composite here where this is f plus y, and this is, if this was g, this is g. In other words, we post-compose. And you see that here is our little fix here. It's what's happening right here in the middle. So what this can be described as is a Kleisli composite, but indexed over our category of outputs here, which are finite sets. And so our theorem here, and I think I should, which is David's theorem, is that the wiring diagrams are the same thing as the Grothendieck construction of over any finite sets, let's say A output, of the Kleisli category A out plus dash. Now, those of you who know about Grothendieck constructions knows that there are both co- and contravariant Grothendieck constructions. This one is, drumroll please, the contravariant Grothendieck construction on this op. That double opposite handles the way that these ones go backwards and these ones go forwards. So if you see here, we say how the outputs of the outside go into the inside, but we say how the inputs of the inside go into either the inside or the outside. And that opposite is handled by this double contravariance here. So Kleisli is a covariant functor into cat. You're not supposed to take contravariant Grothendieck constructions of this, but it's also a contravariant functor on finite sets opposite. So you can. There's a little bit of twisting around, but it's all going to work out. Okay, so the one thing I want to notice now is that we're trying to wire together these systems. We understand wiring diagrams. They're given by this kind of weird, twisted Grothendieck construction. And wiring diagrams also look a lot like something else. So remember, a wiring diagram looks like this, right? You have W out from B out to A out, and then you have W in from A in to A out plus B in. And the system had these two functions. Now, if you look at these, they almost look categorically dual. There's one difference, is that S is the same on both sides here. So if I instead have one of them be positive and one of them be negative, now they're totally different. And this general thing here is called a lens. So this is a lens. And we'll say it's a lens of the form S plus, S minus, to from I-O. And so lenses are given by a similar Grothendieck construction. So given, so we have a map from the co-Kleisli category now. And this is even less familiar than the Kleisli category, which is the categorical dual of the Kleisli category. The Kleisli category has maps that come out and they have some kind of extra effect. The co-Kleisli category uses some kind of extra context. And here the extra context is going to be by multiplication. So we have set op to cat. It's a categorical dual. And this sends a set to the co-Kleisli category here, which has morphisms of the form C cross X to Y. So like something up here. And it sends every function here it sends this to, well, sorry, it's going to go the other way because it's contravariant. And so here it takes C prime cross X to Y. I'll call it G. And it sends it upwards here to C cross X. We use F here, which is this one, to go to C prime cross X. And then we go to Y to G. So this handles what's called lens composition. So if you're familiar with the world of optics, as some functional programmers are, and they're extremely cool, then this gives you what you know to be a lens, and what I was calling a wiring diagram is a prism. And so how do we wire together systems? Well, given any such index category, oh, I didn't tell you what the category, the lens here is defined to be the Grothendieck deconstruction of this indexed category. So this has maps going either way. Okay. So this leads us to our notion of generalized lens, which is due to David. That's not me, David. That's David Spivak. Let's see. This one. So the generalized lens construction just says, like, look, all we ever needed here was an index category, and then we just, sorry, this has to be up. All we ever needed was an index category, and we could do this. In fact, what we want to do is have systems that can be put together side by side. So we also want a monoidal index category. I'm going to ignore that for the rest of the talk, as I have been until now. So given something of this form, we can define A lenses. So this is an index category. The category of A lenses, or lens A, is defined to be the Grothendieck deconstruction of A op, the pointwise opposite. And the reason we take that opposite is because we have this backwards flow here. It's the same backwards thing that was happening with the wiring diagrams, just in the opposite direction. So one way to think about what lenses do is they allow you to pass forward information, that's this bottom part, and they allow you to pass back information in a way, so this is from I to S minus here, in a way that uses what was upstream down here. So this gives us the general category of lenses. Now, you can see that a dynamical system, an open dynamical system, is a special kind of lens. So an open dynamical system is a special kind of lens. Namely, it is a lens of this form. SS to IO. Now what's nice about this is that because it's a lens, and because lenses compose, we can take any lens over here, and the composite is a new dynamical system. And this is how we plug dynamical systems into each other, because we can turn a wiring diagram into a lens. And we do that by the functoriality of this construction. So if we have C op to cat A, and then we have some functor of index categories from A to B, which is a diagram of this sort, then we get a functor from lenses in A to lenses in B. In particular, there's a functor taking opposites of finite sets to the powers of a single object. If we have an object of values in mind, then we can send, so in particular, e.g., if we have, let V be a set, then we have this thing, V to the power of, from fin op to set. And since this is dual, it sends prisms or wiring diagrams to lenses. So this gives wiring diagram to lens. And this is the way we turn a wiring diagram to a lens. We say we pick a set of values to flow on the wires, and then we apply this functor, turns it into a lens. It's a purely formulaic functor. So this is a definition. So this is a generalized lens. Lens. And this is Spivak. So this is David's definition here. And then, once we've turned it into a lens, we can just compose it with our dynamical systems, and that wires them together. So that's that general framework. That's how we get to these sort of very abstract notions of lens. Why do we need lenses in different categories? Well, it's because we want to vary the category we're using to get these functors between our dynamical systems categories at the end of the day. So finally, I'm ready to tell you what a dynamical system is in general. And then we'll see some examples. Def and open. Oh. Even. So we have some kind of indexed category, and the way we think of it as this is our category in which our states are going to live. And this is a category, this sends to every kind of object there, every space, a bundle. And that bundle is the possible inputs given an output, or the possible directions you could take in a given state. It's going to be of the form it's a lens of the form SS IO in lens A. So explicitly, this is a readout to O and an update, and it goes from R star I, where R star is, this is a contravariant functor into category. So we have a pullback of bundles. We pull back I over, so it lives over S, then we map into S. But there's one problem with this notion, is that now I don't know exactly that this S and this S are the same. And in fact, we don't always want them to be the same. Because if you remember all the way up here, in the continuous case, we go from S to TS. So we need an extra bit of data, and this extra bit of data is a section of this index category. So the section I'll write as epsilon. And epsilon a section. And that means that epsilon C is in AC for all C. And that given F from C to C prime, we get epsilon F from C to F star C epsilon C prime. So an example of this is, e.g., we could send S maps to S. And this works for the Koch-Kleisley example of discrete lenses. Discrete-time. But we could also do S maps to the tangent bundle. And that works for our continuous time lenses. So here I can now give a few examples of this. So we have a discrete time one here. We've already seen what these look like in the open case. It is an automaton. And this has dynamics here. We have S to O, the readout, and then we have S cross I to S, the update. So here, A is co-Kleisli, and epsilon is sending S to itself. But then we can do something else. So this would be an open Markov process. And it outputs deterministically. So all these things have this property, they output deterministically, and that is kind of important for having things compose. But the update here goes to distributions on states. And similarly, we can have this one, where it's now into PS, the power set. And finally, we have the open continuous time systems. And they work like this. It's a little more interesting. Here, we have a bundle of inputs like this. And we have states here. And here, we're going to have R. And here we have the tangent bundle. And what we do is we pull back over R. So this little square is a pullback. And then the map goes this way. And this is U. So R and U is our data here. And that expresses the open continuous time dynamical system. And all of these things can be wired together using the wiring diagrams. And in particular, you might wonder when we can do something like this. So in this case, we had an operation on sets, and we stuck it there. So I'll mention when we can do that now. Are there any questions about this general definition? A little blistering fast in the middle there. There's a lot of ground to cover. Yeah.
I missed where the autonoma that you defined when you strung them together became a closed system.
Yes.
I missed the transition in your presentation to when you started talking about open systems.
Yes, so those agent, are they still up here? These ones, the individual agent and environment, each one of those is open.
Okay, so do you have a way of looking at subsystems here that's bringing out the... I don't see where the open part came in really very clearly.
The open part is that each of these is going to be a pair of functions.
In your formulation, the formulation looks like it takes everything into account. I don't see subsetting or taking pieces out in the formulation.
We don't talk about taking pieces out, we talk about putting them together.
Yeah.
So in other words, if you know how to put them together, you can put them together. It's a different kind of question that's is much harder in general to figure out how to take something that's already in a black box and see how it works on the inside.
These are actually closed systems because you've taken the whole universe into account, but you actually have to look at a part of it that actually be looking like an open system.
They are open in the sense that they await inputs and they yield outputs that could be used in other systems. So it's not the whole universe, because the universe doesn't have any inputs and it doesn't have any outputs. There's nowhere to go. So a special case of an open system is a closed system. And you can always close off an open system if you have a way of turning outputs to inputs, if you can form a feedback loop. And that's the case up here. We form a feedback loop so we can close the system off.
There was no feedback in these other ones?
It's not part of the assumption that there is a feedback. We can put it in, though. And it's, of course, most interesting systems have that. Okay. So the last thing I want to mention, because I said something about implementing in Haskell, is that there's a general way to get the discrete time parts of these, the discrete time open systems, to get them composing and to get it without having to do a lot of duplicate coding. And the idea is an M dynamical system for monoidal monad So a monoidal monad is any monad in Haskell with one extra property. This code is equal to this code. So you see that this is super duper not true for the I/O monad. So if your systems are doing I/O, you can still use this framework totally. You can't express this constraint in Haskell, but you're not guaranteed that it's going to give you the same result. Depending on how you put those boxes in at different times, you'll get different outputs, because if one of these says print hi and one of these says print bye, one way of putting the boxes in is going to say bye hi and the other one's going to say hi bye. But in all the examples here, so for example, probability distribution monad, power set monad, there's also various other forms like probability distributions on a reward and your set, which is useful for hierarchical planning. This comes up in the morphisms, which I'm not going to get to. They all satisfy this property. So then, this is the general idea here. Just to reiterate, you go into I and S, and you go to S to O. And these can be composed using wiring diagrams and also with lenses in the general sense. So if you have a lens, and I mean a bimorphic lens in Haskell, you can compose it on one side of these as long as it also has this monad out here. And the nice thing is that given any monoidal morphism between these monads, so in other words, given any way of, say, turning a deterministic one into a probabilistic one, which you have by taking delta distributions, you can turn any dynamical system of one into the other. So given monoidal morphism M to N, we get a functor dynamical systems in M to dynamical systems in N. And therefore, in particular, since the unit of a monad, or aka return, is always monoidal, we always get a morphism from dynamical systems into M-dynamical systems. In other words, we can always promote a dynamical system which is deterministic into any of these other ones. And the nice thing about this framework is when you wire them together here, it automatically adds up all the probabilities and calculates it for you. And it uses all the same code every single time. It's sort of the magic of do notation. It looks as if you weren't doing it at all. That's it. That's all I got. Is this written anywhere?
Yeah.
It's in the process of writing. So the definition is set, but the theory of it is very much in flux. It's a work in progress. So okay. I'm on it.
So in computer science, we would call this a commutative monad?
Yes.
And then how does the commutativity come up in the definition of the M-dynamical system?
That's a great question. I sort of, everything here has to be done in a monoidal way, or we can't. I'm sorry. The question was, I said monoidal monad, but the picture here just has the monad applied to something. Where's the monoidal part, or aka commutative monad in Haskell? And the answer is, when you put together boxes, you need to join those systems up together, and that uses a monoidal product. So what you need is the Kleisli category to be a monoidal category, and that only happens when it's commutative, like this.
I'm not sure, like, this question might be way off the wall, but I'm not sure, like, why there's just the tangent bundle over S. And not something like, I guess, higher order, like the jet bundle.
This is a first order
I see.
system, yeah.
First order like PDE.
Yes,
I see. Okay.
yes. Yeah, you can of course replace it. In fact, you can replace it with a jet bundle if you want.
Have you pushed it out? Like I don't know how difficult it is to like go to the next step, but you're working in the category of manifolds. So then you push that up to like the Smith spaces, I guess, or like
Diffeological spaces or something like that.
Yeah.
I personally prefer to work there, but if I say that, I feel like I'll scare everyone. So, so these are a general instance of what like to call a dependent lens, which is a generalized lens for the slice construction. And if you do it in diffeological spaces, this becomes an instance of a dependent lens, and all sorts of other interesting things become dependent lenses. So.
Have you thought about stochastic continuous time dynamical systems?
No, I haven't, but I would like to. I don't really know enough to do that, but I hope to learn. Yeah, if you use diffeological spaces, you can do something that would look like that, but I don't know if it's what people usually mean when they talk about that. So.
We've also heard from Andrea Sessi, is that right? On co-design frameworks for,
Yeah.
I guess they're dynamical systems like things. Have you had any idea about, does your theory fit in at all with sort of the effort of trying to engineer such systems? And
It's a little bit too early to say. It's still very much in the theory portion, but the hope is yes. The hope is that if you have that with these open systems, because you really can at least you can code up simple things in Haskell very, very straightforwardly. Implementing it's going to just take because this is a very general definition, you'll have to know a lot about your specific case in order to really implement it. So it's a little down the road, but yeah.
Do you know if this has any have you seen if this has any application to, I guess, like physics? A lot of this seems very related to the geometry of physics that's on the MLab, especially like the continuous time dynamical system. The bundle picture, I guess.
Yeah.
Looks like really similar to that, and I can't see if that sheds any light on anything. Have you?
Well, it's a differential equation, right? So, I mean, this is a family of differential equations. So, in that sense, yeah. I don't know anything in more specific terms. I'm not familiar with that piece you referenced.
Why don't we thank David again? Thanks.